All right, let's dive straight into this explainer and explore how computer science solves an incredibly common, absolutely crucial problem: finding a specific piece of data and finding it fast. Because, whether we're dealing with just a handful of numbers or a massive database with billions of records, efficiency is literally everything. So today we're going on a little journey. We're going to track the evolution of search algorithms, moving from basic naive logic to randomized guesses, and finally arriving at a brilliantly clever, mathematically guaranteed method for pure speed.
To really ground this, let's imagine a concrete scenario. Picture a giant stack of tests from a massive university class. You need to find the exact median score. The student who did better than exactly half the class but worse than the other half. Now, your first instinct might be to just sort all the tests from highest to lowest and pull the middle one, right? But sorting every single paper just to find that one middle score, that is a massive waste of time and computational power. And that introduces the core challenge we're tackling today.
So here's our quick roadmap. We'll start with the median score problem, then look at finding extremes fast, explore the power of random pivots, introduce the median of medians algorithm, break down 5 steps to efficiency, and finally wrap up with why algorithm speed means business.
Okay, Section 1, the median score problem. Let's begin by actually framing our primary goal, which in computer science is formally known as the selection problem.
To really understand the selection problem, we first need to define a term called order statistics. Now, don't let the name intimidate you. It simply means finding the smallest element in a set of distinct numbers. That's it. So the crucial takeaway here is that whether we want the absolute minimum, the maximum, or that exact media test score, we are just looking for specific order statistics. The key? We aren't trying to organize the entire data set. We literally just want to extract one single item based on its rank.
Moving to Section 2, finding extremes fast. What's really fascinating here is how we can easily handle the absolute extremes before we even attempt to look for that tricky middle ground.
Think about it. If we just want the absolute minimum or maximum test score, it requires what we call n-1 comparisons. It's kind of like running a massive sports tournament. To find the absolute worst score or the absolute best, every single element, except the final winner, has to lose a comparison and enter a loser bracket. So if you have 100 students, you need 99 comparisons to find the lowest score and another 99 to find the highest. But we can actually optimize this. If we search for both simultaneously by pairing elements up right from the start, we reduce the total comparisons we have to make. Pretty neat, right? But what happens when we don't want the extremes? What happens when we want that median?
That brings us to Section 3, the power of random pivots. Let's look at a really clever shortcut that completely avoids sorting that whole pile of test scores, called randomized selection.
To make this shortcut work, we have to define a super important concept, the pivot. A pivot is, well, it's simply an arbitrary line in the sand. It's just a value we pick from our data, and we use it to divide our array into 2 sides. All the elements smaller than the pivot get shoved to the left, and all the elements larger get pushed to the right.
Imagine a list of unsorted numbers representing our test scores. In randomized selection, we basically just close our eyes and pick one completely at random. Let's say we blindly select the number 10 to act as our pivot point.
Once we apply that pivot, something really powerful happens. We didn't fully sort the whole list, but our pivot, number 10, has moved to its correct final spot in the lineup. It has automatically separated the smaller test scores to its left and the larger ones to its right. Now, if we're looking for the median, and we get incredibly lucky and our pivot lands exactly in the middle rank, boom, we're done. Or if we want a smaller rank, we can completely ignore the right side and just repeat this process on the left side. We are literally throwing away half the problem.
But yeah, there's always a catch. While random pivots give us a fantastic average case time, meaning it's usually very fast and linear, it relies entirely on luck. Guessing the wrong pivot over and over again, like imagine accidentally picking the maximum value every single time, creates a worst-case scenario. If that happens, we only eliminate one single test score per pass. The performance just completely plummets into what we call quadratic time, which is disastrously slow for large datasets. We need a way to remove luck from the equation.
Section 4, the median of medians. To eliminate that bad luck and achieve a guaranteed, bulletproof worst-case linear time, we introduce the absolute hero of our story.
Let's see how this builds on everything we've talked about, starting with this magic number right here, 5. By organizing our students or our data into small, manageable teams of exactly 5, we can mathematically guarantee we never hit that terribly slow worst-case scenario.
Actually, scratch that whole guessing part from earlier. Instead of guessing a random pivot, we are going to calculate a highly strategic one.
Grouping by fives is kind of magical because of the math it unlocks. When we find the medians of those tiny groups of 5, and then find the median of those medians, it guarantees that our chosen pivot is remarkably balanced. At every single pass, we are mathematically guaranteed to prune away at least 3/10 or 30% of the data we no longer need to search. Think about that. We never have a useless pass. We always shrink the haystack by at least 30%, guaranteeing extremely fast linear time even if we have the absolute worst luck in the world.
Moving to Section 5, 5 Steps to Efficiency. Let's break this seemingly complex algorithm down into a really easy, logical flow. Okay, here are the 5 phases. Step 1, break the unsorted array into those small groups of 5. Step 2, quickly sort just those tiny groups to find their mini-medians. Step 3, take all those mini-medians and find the ultimate median of those medians. That becomes our super pivot. Step 4, we partition our main data around that super pivot just like before, separating the smaller and larger numbers. And step 5, we recurse. We just repeat the whole process on whichever side contains the exact order statistic we're hunting for. If you picture the data divided into these neat little columns of 5, it makes perfect sense. We can very quickly sort these tiny columns. Once they're sorted internally, it lets us just pluck the medians right out of the middle row. We then take just that middle row to find our super pivot. It is a brilliant, elegant way to sample the data evenly without having to sort the entire massive grid.
Now, for the beginner programmers tuning in, don't let code snippets intimidate you. This logic is actually beautiful. Once we partition the data around that perfect super pivot, the algorithm just checks its position. Did the pivot land exactly where we wanted? If yes, great, we return it. If not, we simply ask the code to recurse, to basically run itself again, but only on the side of the data that holds our answer. The rest of the data, permanently discarded.
Finally, Section 6, Algorithm Speed Means Business. Let's zoom out from the code for a second. Why does this theoretical efficiency actually matter in the real world, outside of a computer science classroom? Why even go through the trouble of groups of 5?
Well, because upgrading from a slow, quadratic worst-case algorithm to a guaranteed linear one translates directly into real money and system stability. It prevents massive bottlenecks when millions of users hit a database at the exact same time. It directly reduces server compute costs because the processor is literally doing a fraction of the work. It ensures predictable scaling for a business, and most importantly, it entirely eliminates those worst-case crashes under load. If your system relies on random guessing and gets unlucky during a huge traffic spike, the server crashes. The median of medians algorithm makes that impossible.
Which leaves us with a really fascinating perspective on optimization. The core lesson here isn't just about writing better computer code. It's about how much time, energy, and money we waste trying to perfectly organize absolutely everything when we really only need to find one specific thing. If you only need the median, don't sort the whole pile. So it begs the question, where else could we be working smarter, pruning the useless data, and just finding our answer?